In this problem, I'm going to do a work problem, and this work problem will involve finding the amount of work involved with lifting a bucket of sand to the top of a building. So suppose you are lifting a bucket that holds 40 kilograms of sand to the top of a 700-meter tall building using a rope that has a density of 0.3 kilograms per meter. Find the work done lifting the bucket to the top of the building. So first of all, let's draw our building. Okay, so we have a building that looks like this, and it is 700 meters tall. So I'm going to put 700 up here and 0 down here. And I am going to let this be an x distance. So when x is 0, we are at the bottom of the building. When we are x is 700, we are at the top of the building. So let's start with our work formula. Work is equal to the integral from a to b of a force function exerted over a distance, so f of x dx. Well, we remember that force is defined as being mass times acceleration. And in this case, we're dealing with acceleration due to gravity. And so this is a constant 9.8. So we could rewrite this integral as 9.8 times the integral from a to b of some mass function now, dx. So the key here is we need to determine the mass. And so to do that, we have to consider the mass of the bucket. So mass is going to be equal to the mass of the bucket added to the mass of the rope. Now, the mass of the bucket was given to us as 40 kilograms. So this becomes 40 kilograms is the mass of the bucket. And the rope is just a little bit more difficult to figure out because we're not given the mass of the rope, but we are given its density. And so we also have to remember that mass is equal to density times distance. So the density of the rope was given to us as 0.3 kilograms per meter. So we have 0.3 kilograms per meter times the number of meters, which is 700. Now, that's not all there is to the story, because as we pull the rope up to the top of the building, we don't have as much rope hanging down the side of the building. Some of it is resting peacefully on the top of the building. So every foot that we pull the rope up, we have less mass. And so the mass of the rope per foot is 0.3 kilograms per meter times x meters. And so that's what this x represents. X represents the number of meters. So when x is equal to 0, we're at the very bottom of the building on the ground. So we would subtract 0 kilograms from the mass of the rope, and we would just have the 0.3 times 700. When we are 1 meter, when we've pulled the bucket up 1 meter, we would subtract the 1 meter's worth times 0.3 kilograms per meter. That's sitting on top of the building, etc., etc. So that means that the rope, the mass of the rope is 0.3 times 700, which is 210, minus 0.3x. So the total mass is the mass of the bucket, which is 40, plus the mass of the rope, which is 210, minus 0.3x. And that, of course, then becomes 250 minus 0.3x. So let's put everything together now. Go back to our integration formula. Work is equal to 9.8. And the bounds of integration are from 0 to 700. And our function now is 250. 250 minus 0.3 x dx. Now it's just time to integrate. So that's the hard part. The hard part is coming up with the integral that you need to integrate. But let's just go ahead and finish this. So work then will be equal to 9.8 times 250x minus 0.15x squared, evaluated from 0 to 700, or 9.8. And if I did my arithmetic correctly, and we put the 700 in here, minus 0.15 times 700 squared, and then putting 0 in, we just get a big fat 0. Work is going to be equal to 9.8 times 101,500, and then multiplying by 0.8, we end up with the total amount of work being done is 994,700, and I believe that would be joules. All right, and that is the bucket problem.